Hey everyone, and how goes it? Welcome back to Computer Science 311. Today we're going to discuss threads and concurrency. In previous lectures, we assumed that a process was an executing program with a single thread of control. Now, virtually all modern operating systems provide features enabling a process to contain multiple threads of control. Identifying the opportunities for parallelism through the use of threads is becoming more increasingly important for modern multi-core systems that provide multiple CPUs. A thread is a basic unit of CPU utilization, and it's composed of a thread ID, a program counter, set of registers, and a stack. It shares with other threads belonging to the same process its code section, data section, and other operating system resources such as open files and signals. Most software applications that are run on modern computers and mobile devices are considered multi-threaded. Now, some of the examples of how an application uses multithreading is an application that creates photo thumbnails from a collection of images may use a separate thread to generate those thumbnails. A web browser might have one thread to display images or text while another thread retrieves the information from the network. A word processor may have a separate thread for displaying graphics, another thread for responding to keystrokes from the user, and a third for performing spelling and grammar checks in the background. In certain situations, a single application may be required to perform several similar tasks. For example, if we have a web server that accepts client requests for a web page, images, sound, and so forth. Now, a busy web server may have several, perhaps thousands, of clients concurrently accessing it. If the web server ran as a traditional single-threaded process, it would be able to service only one client at a time. And a client might have to wait for a very long time for its request to be serviced. Now, one solution is to have a server run the single process that accepts this request. However, process creation is time-consuming and resource-intensive. If a new process will perform the same tasks as an existing process, why incur all that overhead? It is generally more efficient to use one process that contains multiple threads. So in addition, most operating system kernels are typically multi-threaded. So for an example, on the Linux system, several kernel threads are created whenever the system boots. Each thread performs specific tasks, such as managing devices, memory management, or interrupt handling. Many applications can also take advantage of multiple threads, including basic sorting, trees, graph algorithms. In addition, programmers who solve contemporary CPU-intensive problems in data mining, graphics, and artificial intelligence can leverage the power of modern multi-core systems by designing solutions that run in parallel. Now this leads us to the benefits of multi-thread programming, and it can be broken down into one of four categories: responsiveness, resource sharing, economy, and scalability. So for responsiveness, multi-threading an interactive application may allow a program to continue running even if part of it is blocked or is performing some lengthy operation. Thereby, it increases the responsiveness to the user. The quality is especially useful in designing user interfaces. So for instance, consider what happens when a user clicks a button that results in a performance of a time-consuming operation. A single-threaded application would appear unresponsive to the user until the operation has completed. In contrast, if the time-consuming operation is performed in a separate asynchronous thread, the application remains responsive to the user. So this also relates in video games where you have a load screen showing the user that it is loading the next level or the next resources required to run the next part of the game. That is multi-threaded. Resource sharing. Now, a process can share resources only through techniques such as shared memory and message passing, which we've discussed before. Such techniques must be explicitly arranged by the programmer. However, threads share the memory and the resources of the processor to which they belong to by default. The benefit of sharing code and data is that it allows an application to have several different threads of activity within the same address space. The economy. Allowing memory and resources for process creation is costly. Because threads share the resources of a process to which they belong, it is much more economical to create context-switched threads. Empirically gauging the difference in overhead can be difficult, but in general, thread creation consumes less time and memory than process creation. Additionally, context switching is typically faster between threads than between processes. Finally, scalability. The benefits of multithreading can be even greater in a multiprocess architecture, where the threads may be running in parallel on a different processing core. Now, early on in the history of computer design, in response to the need for more computing performance, single CPU systems evolved into multi-CPU systems. Now, a later but similar trend in system design was to place multiple computing cores on a single processing chip, where each core appears as a separate CPU to the operating system. We refer to such systems as multi-core systems, and multithreaded programming provides the mechanism for more efficient use of these multiple computing cores and improved concurrency. Now this leads us to a distinction between the difference between parallelism and concurrency. A concurrent system supports more than one task by allowing the task to make progress. This is in contrast to a parallel system that can perform more than one task simultaneously. Thus, it is possible to have concurrency without parallelism. And here's a demonstration to show the two. Concurrency allows multiple tasks to make progress. However, on the other side, different tasks can be running at the same time if they are parallel. Now, understanding the difference also adds in a level of difficulty for programmers. Now, in general, there are 5 areas that present the most difficulty when it comes to programming: dividing the activities, balance, data splitting, data dependency, and finally testing and debugging. Now, dividing up the activities, otherwise known as identifying the task, this involves examining applications to find areas that can be divided into a separate or concurrent tasks. Ideally, what you want are tasks are independent of one another and thus can run in parallel or on individual cores. Ideally, tasks are independent from one another and thus can run in parallel on individual cores. Balance. When we're identifying tasks that can run in parallel, programmers must also ensure that the task performs equal work of equal value. In some instances, a certain task may not contribute as much value to the overall process as some of the other ones. Using separate execution cores to run that task may not be worth the cost. Data splitting. Now, just as applications are divided into the separate tasks, the data accessed and manipulated by those tasks must also be divided to run on separate cores. This then leads us to data dependency. The data accessed by these tasks must be examined for dependencies between 2 or more of them. When one task depends on data from another, programmers must ensure that the execution of these tasks are synchronized. We examine this a lot further in a future chapter. And finally, testing and debugging. Now, when a program is running in parallel on multiple cores, there are many different execution paths. This makes testing and debugging much more difficult. Now, when looking at parallelism, it can be broken into 2 major types: data parallelism and task parallelism. Now, data parallelism focuses on distributing a subset of the same data across multiple computing cores and performing the same operations on each one of the cores. On the other hand, task parallelism involves distributing not the data, but the tasks, or the threads, across multiple computing cores. Each thread is performing a unique operation. And as you can see, this is the ways that we can look at both data and task parallelism in relation to the cores and their data. Now with concurrency and parallelism discussed, we introduce Amdahl's law. Now Amdahl's law is a simple formula that identifies potential performance gains from adding additional computing cores to an application that has both serial, which is the non-parallel parts, and parallel components. So given this inequality, S is the portion of the application that must be performed serially. So in other words, the non-parallel parts of the application. The N corresponds to the number of processing cores. And so, with this inequality, we gain a speedup that is less than or equal to 1 over the serial parts plus 1 minus the serial parts over that N. Keep in mind, 1 minus the serial parts corresponds to what is in parallel. So, for example, if we have an application that is 75% parallel and 25% serial, moving from 1 to 2 cores, the result is the speedup of 1.6 times. Now, so far, our discussion about threads has treated them in the generic sense. However, there is support for threads that may be provided at both a user level or the kernel level. User threads are supported above the kernel and are managed without the kernel support, whereas the kernel threads are supported and managed directly by the operating system. Now, there has to be a relationship that exists between the user threads and the kernel threads. Specifically, there are 3 common ways of establishing those relationships from user to kernel, and those exist are many-to-one, one-to-one, and also many-to-many models. The many-to-one model maps many user-level threads to one kernel thread. Thread management is done by the thread library in the user space, so it is efficient. However, the entire process will block if a thread makes a blocking system call. Now keep this in mind, one thread can access the kernel at a given time. Multiple threads are unable to run in parallel on multi-core systems. So like for instance, if this thread right here made a blocking call to the system, it would block all of the other ones because it would block the kernel thread. Now there are very few systems that currently use this model. Now another way that we can approach mapping the user threads to the kernel threads is using a one-to-one model. And in this model, each user thread maps directly to a kernel thread. This provides more concurrency than the many-to-one model by allowing another thread to run when a thread makes a blocking call. It also allows multiple threads to run in parallel on multiple processors. Now, the drawback to this model is that creating user threads requires creating a corresponding kernel thread, and a large number of these kernel threads may overly burden the performance of a system. So now we introduce the many-to-many model, and this allows many user threads to be mapped to many different kernel threads. This multiplexes many user threads to the smaller or equal number of the kernel threads. The number of kernel threads may be specific to either a particular application or to a specific machine. Now, the many-to-one model allows the developer to create as many user threads as they wish, and it does not result in parallelism because the kernel can only schedule one kernel thread at a time. The one-to-one model allows greater concurrency, but the developer has to be careful that they do not create too many threads. Now, the many-to-many model suffers from neither of these shortcomings. Developers can create as many user threads as necessary, and the corresponding kernel threads can run in parallel on multiprocessors. Also, when a thread performs a blocking call, the kernel can schedule another thread for execution. One variation of many-to-many is called the two-level model. Now, this model still multiplexes many user-level threads to a smaller or equal number of kernel threads, but it also allows user threads to be bound to a kernel thread. Now, the many-to-many model appears to be the most flexible of the models discussed, but in practice it is difficult to implement. In addition, with an increasing number of processing cores appearing on most systems, limiting the number of kernel threads has become less important. As a result, most operating systems now use the one-to-one model. Now, in terms of developing software, a thread library provides the programmer with an API for creating and managing threads. Now, there are two ways that we can implement a thread library. The first approach is to provide a library that's entirely in the user space with no kernel support. All code and data structures for the library only exist in the user space. The second approach is to implement a kernel-level library supported directly by the operating system. Now, in this case, code and the data structures for the library exist in the kernel space. Invoking a function in the API for the library typically results in a system call to the kernel. Now, we're going to go over a couple of various thread libraries, but before we could do that, we need to introduce there's two general strategies for creating multiple threads. One's called asynchronous threading, the other is called synchronous threading. With asynchronous threading, once the parent creates a child thread, the parent resumes its execution so that the parent and child execute concurrently and independently of one another. Because the threads are independent, there are typically little data sharing between them. Now, on the other side, asynchronous threading is the strategy used in multi-threaded servers and is commonly used for designing responsive user interfaces. Synchronous threading occurs when the parent thread creates one or more children and then must wait for all of its children to terminate before it resumes. Now, one example of these libraries are called Pthreads, and these provide either user or kernel level threading. Now, there are a number of systems that implement Pthread specifications, and most are Unix-type systems that include Linux and Mac. There's also threads in Java. Now, threads are a fundamental model of programming execution in Java, and the Java language and its API provide a lot of features for creating and managing threads. Now, all Java programs comprise of at least a single thread of control. Even the most simple Java program consisting of only a main method runs as a single thread in the JVM. Java threads are available on any system that provides a JVM, including Windows, Linux, and Mac. Now, as multicore processing continues to grow and applications are starting to contain hundreds, maybe even thousands of threads, we have to design applications in a very strategic way. Now, designing such applications is not easy, and programmers must address not only challenges mentioned before, but also additional challenges that relate to programs' correctness that is covered later on. One way we can address these difficulties and better support the design of concurrent and parallel applications is to simply transfer the creation and management of threading from the application developer to the compilers and to the runtime libraries themselves. This strategy is called implicit threading. Now, these strategies require application developers to identify tasks that can run in parallel. Now, this is different from identifying threads. A task is usually written as a function, which the runtime library then maps to a separate thread, typically using the many-to-many model. The advantage of this approach is that the developers only need to identify the tasks, and the libraries themselves will determine the specific details of the thread's creation and its management. Now, one way we can address implicit threading is by using a thread pool. The idea behind this is to create a number of threads at startup and then place them in a pool where they sit and wait for work. Now, rather than creating a thread, it submits a request to the thread pool and then resumes waiting for additional requests. Now, thread pools provide several benefits. First, servicing a request with an existing thread is often faster than waiting to create a thread. A thread pool limits the number of threads that may exist at any one point. This is particularly important on systems that cannot support a large number of concurrent threads. Also, separating the task to perform from the mechanics of creating the task allows us to use different strategies for running the task. So, for example, the task could be scheduled to execute after a time delay or to execute periodically. Now, the number of threads in the pool can be set heuristically based on factors such as the number of CPUs in the system, the amount of memory, and also the expected number of concurrent client requests. More sophisticated thread pool architectures can dynamically adjust the number of threads in the pool according to certain usage patterns. Now, Java utilizes thread pools. Now, the java.util.concurrent package includes an API for several varieties of thread pool architectures. Like, for instance, you can have a single thread executor that creates a pool of only size 1. You can have a fixed thread executor which creates a thread pool with a specific number of threads. And finally, you can have a cached thread executor that creates an unbounded thread pool, reusing threads in many of the instances. Another way we can approach implicit threading is the fork and join model. Now, if we remember, this method was previously discussed. The main parent thread creates forks. In other words, one or more children threads that then waits for the children thread to terminate and join in with it, at which point it can retrieve and combine their results. This is a synchronous model that is often characterized as explicit thread creation, but is also an excellent candidate for implicit threading. So basically, if we were to look at this hypothetical task that we're going to fork and join in parallel, then it can be viewed as this, where basically it is recursively making forks that are then joining back to the original task. Another example is called OpenMP, and this is a set of compiler directives as well as an API for programmers that is written in C, C++, or even Fortran. This provides support for parallel programming in shared memory environments. What OpenMP does is identify parallel region as blocks of code that may be run in parallel. Application developers insert compiler directives into their code to indicate the parallel regions. So this would indicate a parallel region. Now also, the Grand Central Dispatch, the GCD, is a technology that was developed by Apple for its macOS and iOS operating systems. Now this is a combination of a runtime library, an API, and language extensions that allow developers to identify sections of code, in other words known as tasks, to run in parallel. Now GCD schedules its tasks for runtime execution by placing them on what's called a dispatch queue. When it removes a task from the queue, it assigns that task to an available thread from a pool of threads that it manages. The GCD identifies two types of dispatch queues, serial and concurrent. The tasks placed on the serial queue are removed first in, first out order. Once the task has been removed from the queue, it must complete execution before another task is removed. Each process has its own serial queue, known as its main queue, and developers can create additional serial queues that are local to a particular process. Tasks that are placed on the concurrent queue are also removed in, first out order, but several tasks may be removed at a time, thus allowing multiple tasks to be executed in parallel. Now we've discussed what a thread is, and we've also discussed how we may implement threads in our software development, we need to discuss some issues that come about from threading. Now we have described how the fork system call is used to create separate duplicate processes. Now the semantics of using the fork and the exec system calls change in multi-threaded programs. So if one thread in a program calls fork, does the new process duplicate all threads? Or is the new process single-threaded? Now some Unix systems have chosen to have two versions of fork, one that does duplicate all the threads, and another that duplicates only the thread that's invoked with the fork system calls. Now along with that, if a thread invokes the exec system call, the program specified in the parameter to exec will replace the entire process, including all of the threads. Another issue that comes about is signal handling. Now, a signal is used in Unix systems to notify a process that a particular event has occurred. A signal may be received either synchronously or asynchronously, depending on the source and the reason for the event being signaled. All signals, whether they're synchronous or asynchronous, may follow the same patterns. A signal is generated by the occurrence of a particular event. The signal is delivered to a process, and finally, once delivered, the signal must be handled. Now, handling signals in a single-threaded program is very straightforward. Signals are always delivered to the process. However, delivering signals is more complicated when it comes to multi-threaded programs, where a process may have several threads. So, where should a signal be delivered for multi-threads? Well, there's a couple of options we could take. First, we can deliver the signal to the thread to which the signal applies. Second, we deliver the signal to every thread in the process. Third, we deliver the signal to certain threads in the process. Or finally, we assign a specific thread to receive all signals for the process. The method for delivering a signal depends on the type of signal generated. So for example, a synchronous signal needs to deliver to the thread causing the signal and not to the other threads in the process. However, the situation with asynchronous signals is not quite as clear. Now another issue is, how do we cancel threads? Now thread cancellation involves terminating a thread before it has completed. So for example, if multiple threads are concurrently searching through a database and one of those threads returns the result, the remaining threads might be canceled. Another situation might occur when a user presses a button on a web browser that stops a web page from loading any further. A thread that is to be canceled is often referred to as a target thread. Cancellation of a target thread may occur in two different ways: asynchronous cancellation and deferred cancellation. In asynchronous cancellation, one thread immediately terminates the target thread. In deferred cancellation, the target thread periodically checks whether it should terminate or allow it an opportunity to terminate itself in an orderly fashion. Requesting to cancel the target thread depends on how the target thread is set up to handle that request. Like for instance, Pthreads supports 3 different cancellation modes. Each mode is defined as a state and a type as illustrated in this table. The default cancellation type is deferred cancellation. However, cancellation only occurs when a thread reaches a cancellation point. One way to establish a cancellation point is to invoke a specific function, like for instance, pthread test cancel. Now in addition, specifically, Pthreads allow a function known as a cleanup handler to be invoked if the thread is canceled. Now this function allows any resources a thread may have acquired to be released before it is terminated. Another issue is thread local storage. Now threads belonging to a process share data of that process. Now this data sharing provides one of the benefits of multi-threaded programming. However, in some circumstances, each thread might need its own copy of certain data. We will call this data thread local storage, or TLS. Now, TLS is easy to confuse with local variables. However, local variables are visible only during a single function invocation, whereas TLS data are visible across function invocations. Additionally, when the developer has no control over the thread creation process, for example, when using implicit techniques such as a thread pool, then an alternative approach is necessary. Now, in some ways, you can consider TLS to be similar to static data. However, the difference is TLS data are unique to each one of the threads. Now finally, the last issue that we have to consider with multi-threaded programs concerns with communication between the kernel and the thread library. Many systems implementing either many-to-many or the two-level model place an intermediate data structure between the user and the kernel threads. This data structure is typically known as the lightweight process or the LWP. Now, to the user thread library, the LWP appears to be a virtual processor on which the application can schedule a user thread to run. Each LWP is attached to a kernel thread, and it is the kernel threads that operating system schedules to run on the physical processor. If a kernel thread blocks, such as waiting for an I/O operation to complete, the LWP blocks as well. Now, the scheme for communication between the user thread library and the kernel is known as the scheduler activation, and it works as follows. The kernel provides an application with a set of virtual processors, LWPs, and the application can schedule user threads onto an available virtual processor. Furthermore, the kernel must inform an application about certain events. This procedure is known as an upcall. Upcalls are handled by the thread library with an upcall handler, and the upcall handlers must run on a virtual processor. So one event that can trigger an upcall is when an application thread is about to block. In this scenario, the kernel makes an upcall to the application informing it that a thread is about to block and identifying the specific thread. The kernel then allocates a new virtual processor to the application. The application runs an upcall handler on this new virtual processor, which saves the state of the blocking thread and relinquishes the virtual processor on which the blocking thread is running. The upcall handler then schedules another thread that is eligible to run on a new virtual processor. So in this chapter, we have discussed that a thread represents a basic unit of CPU utilization, and that threads belonging to the same process can share many of the process's resources, including code and data. We then discussed the primary benefits to multi-threaded applications and the difference between concurrency and parallelism. After that, we discussed ways that we can implement threading and program development and all of the issues that come about that. And some of those issues we're going to start exploring in more detail in the future. And with all that being said, I'll see you next time.